Hello, welcome to our lab. My name is Hiroshi Fujimoto from the University of Tokyo, Japan. Today, I am happy to introduce all the research activities in my lab. Generally speaking, our lab has three teams: wireless power transfer, an electric vehicle team, and control application team. Let's take a look at the details together. In our lab, dynamic wireless power transfer technology are developing to extend the driving range of electric vehicles. By transferring the energy from the coils inside the load, automatic charging is possible and people do not have to plug in to their EVs every day. Electric vehicle cruising range will be infinity even with a small battery. That is a great future.
Hello, I'll introduce the wireless power transfer WPT team of our laboratory. WPT team consists of 3 assistant professors and 10 students and is the largest group in our laboratory. The main theme of the WPT team is the in-motion charging to electric vehicles. But each member is working on a very different topic, and I'll introduce some examples of them. For example, how can I detect the vehicle before charging without sensors? And what is the control method which is robust to circuit parameter errors? And how can I detect the foreign objects which interferes the power supply? Some of the topics we are currently working on. We'll show you the many experimental setups related to D-WPT in the technical tour. Please enjoy it.
This is a mini-scale test room. We mainly use this room to fabricate and measure experimental instruments. This is a 3D printer, and this is a board processing machine. We can build a WPT setup using these machines, as this mini WPT coils and test low power experiments. Small scale experiments like this can be conducted in this room. There is a set of soldering tools. Many of the measurement instruments used for WPT experiments are stored here, such as LCR meters and EMF measuring tools. The PCs are used for simulations. In this analysis PC, electromagnetic field analysis simulations are mainly performed. These PCs are owned by our laboratory, therefore the members can use freely.
Let's go to our garage. We're researching on the electric vehicle at that area. You can see here, that is our electric vehicle test field, in which only our lab can test the vehicle every day. And then we can access to our vehicle here directly. This is Professor Shinji and Dr. Nagai here.
Hi. And the efficiency is very high.
Okay.
Now I'm going to introduce you our unique dynamic wireless power transfer system. Its name is the third generation wireless input motor. This is the third generation wireless input motor, which consists of driver system and the power receiver system. Look at this spare part. It is input motor which can drive the wheel directly. Inverter, active rectifier, and resonance capacitors are also in the wheel. Inverter is used for the motor drive, and the active rectifier and resonance capacitors are used for wireless power transfer. Receiver coil is connected to the resonance capacitor. The coil position is the unique selling point of this system. Generally, onboard coil have to keep the air gap widely due to avoid the collision. In this system, receiver coil moves with the tire and avoid collision to the steps, therefore coil cap can be minimized.
Here are two lanes in our experiment field. One is the no abandoned coil lane. Another is the abandoned coil lane. Here is the no abandoned coil lane. Before the coil abandonment, we use this lane to evaluate the D-WPT performance. And these coils are connected with the inverter, which generates the transmission power. Here is the abandoned coil lane. And this is the coil which we used to abandon into the road pavement. We have already abandoned the coil into the asphalt with the crushed stone and concrete at the bottom.
This is a demonstration of wireless power transfer to a moving electric vehicle. The transmitter coils are placed on the ground, and the receiver coils are attached behind the wheels of the electric vehicle. When the vehicle moves over the transmitter coils, the vehicle receives power and the green bar lights up. By expanding the number of transmitter coils, the vehicle can be charged repeatedly and the cruising range can be dramatically enhanced.
Okay, this is our test field for the electric vehicle. And this is we call it a new garage for the dynamic wireless power transfer. And you can take a look at that coil is already embedded here. And from this field, we are going to go to our old garage. That is, we are developing electric vehicles here. Let's go. Our old garage is approaching. And now we got to our old garage. That is kind of 10 years old. And we can, from here to here, we can store the electric vehicle like 10 vehicles. And we are developing the EV in this facility. Let's go. Get me.
Here, we have a bench for experiments of dynamic wireless power transfer. The road cycle is fixed like this, and the vehicle cycle can be moved up 30 km per hour. By using this bench, we can get highly reproducible data of wireless power transfer. The bench is controlled by this MyWays PH-SPAT4 here, and the speed can be changed freely. The inverter also be connected to the PH-SPAT4, and we can conduct experiments with combined control of the bench and the inverter. Now let's try to move the bench. On this bench, various experiments related to D-WPT are being conducted. We have recently conducted experiments on sensorless vehicle detection, reducing current overshoot at the start of the power transmission, and falling object detection. This is the storage area for experimental vehicles. The vehicles and the experimental equipment are adjusted, and various repair parts are stored here.
As you know, electric vehicle era began. EVs have attractive potential not only for energy and environmental performance, but also for vehicle motion control because electric motors have quick and measurable torque response. Our laboratory is developing motion control technology for EVs to enhance the safety and driving comfort and cruising range.
Hi, I'm Mitsuhiro Hattori, a graduate student of Humanoid Laboratory. I'm working on adaptive cruise control algorithms. We aim to enhance the energy efficiency of electric vehicles by creating optimal velocity trajectory offline. We call our algorithms quadrant dynamic programming. For simulation, the vehicle dynamics block set of MATLAB Simulink is used. For visualization and for experiments, we employ our blue vehicle, FPV5, and the experimental field of our campus. The experiments can be done every day.
We also research vibration suppression control using our experimental vehicle FPV5. This vehicle has an infrared motor unit in the rear wheels. It is inevitable that the vehicle vibrates while driving because of the various disturbance. Using the infrared motor, we can suppress and control the vehicle vibration. To design the vibration suppression controller using infrared motor, we have to know the frequency characteristics of the suspension with the infrared motor. This is the scene when we identified using the experimental vehicle. We are also analyzing the frequency characteristics through the simulation using the multi-body dynamics model we designed.
I would like to introduce our experimental vehicle. So she is called Kanon. She is a fully electric vehicle equipped with a directly driven in-wheel motor in each wheel. Each of in-wheel motor has about 500 Nm maximum torque and also 20 kW of maximum power output. She has almost equivalent power output of ordinary vehicles, but each of in-wheel motor is directly driven. She has very high torque response and controllability. Using this vehicle, we have studied a lot of subjects such as vehicle motion control to achieve safer and more comfortable drive, like traction control, preventing slip of each wheel, and also allocating the torque distribution to achieve safer, smoother cornering. The second research subject we are doing is the ride comfort, such as vibration suppression, like longitudinal direction or vertical direction. The third one is range extension control, that is basically optimizing the speed trajectory at the given, let's say, initial velocity, terminal velocity, and also distance traveling. So now I'm going to show you guys the traction control system developed by our laboratories to show you how the skid of each wheel can be prevented. So the first case is the acceleration of the front wheel driven electric vehicle. The first case is that there's no traction control at all. The driver just steps on the gas. As you can see, there's a tons of sprayed water. If this happens on the real road, there's no way to control the steering, so that is very, very dangerous. Okay, so now he's going to show traction control of electric vehicle. So the second case is that there is a slip ratio controller to limit the slip ratio at a certain value, like 5%, to maximize the traction force. Now he's going to do it, so please watch the front wheels. You see that? It looks really nice, smoothly accelerating. Yeah, he just pressed the accelerator to the metal, but thanks to the traction control, the torque is automatically limited according to the change of wheel speed, and the most efficient, effective acceleration can be achieved like that. Okay, so the second case is the deceleration on the slippery road. The driver applied a brake on the slippery surface without any traction control first. Yeah, look carefully. All the wheels are locked, and also the yaw moment occurs to the clockwise direction. During the such state, the vehicle cannot be turned, controlled at all, and just keep going straight way. So that is pretty dangerous, which should be avoided. And the second case he's gonna apply the traction control and see the difference. Okay, so as you saw, with traction control, the vehicle could decelerate very safely and without any skidding or locking. Okay, so that's pretty much all about our EV team. Not only the environmentally friendliness, we do believe that electric vehicles can be even safer, more comfortable, and more energy efficient. In order to contribute to the true popularization of EVs, we keep creating such novel control strategies as shown earlier. If you are interested in our research, please come visit our website and you will be able to find our presented papers there. Now I conclude the introduction of EVs and thank you very much. Bye.
A control application team in our lab, we are applying our advanced control technology to many industrial applications such as electric airplane, spacecraft, a moving robot, and robot manipulator. Furthermore, we are researching on nanoscale subsystem. The main targets are NC machine tool and big scanner stage for lithography process.
Okay, right here, since this building is the second floor, we have one laboratory for the control application team, where we are researching on the robotics and Rover for the lunar planetary or electric airplane. Let's get in.
As you may know, we have been studying motion control technologies of electric vehicles. And now we are trying to apply these technologies to electric flying mobility. The possible applications are drones, electric airplanes, and flying cars, such as tilt-wing eVTOL aircraft. This is a propeller test bench. It has a propeller, a motor, a load cell, and a wind tunnel. We can measure the basic characteristics of the propeller using this bench. And this experimental setup simulates the tilt-wing eVTOL aircraft. The tilt angle and the flat angle are controlled by the servo motors. We are using this setup to develop a new control method for a stable transition from hover to cruise, and a power reduction system during hovering.
Now I will introduce the IPMSM test bench. Interior permanent magnet synchronous motor IPMSM is applied to various devices such as EVs and trains. IPMSM is implemented into the setup so that we can propose a better control system for IPMSM. Also, high-resolution encoders, a torque meter, and a power meter are installed for advanced assessment. With this setup, we are now researching torque reduction and iron loss reduction.
Our group has studied visual servoing with a robot arm, and now we aim to apply it to space field. And this experimental setup demonstrates a flyby of an asteroid explorer. And this red object is used as an asteroid, and the asteroid moves in a constant velocity by the belt drive, and camera is fixed to the motor on the tripod. It simulates the relative motion in the flyby. And camera tracks the asteroid with the motor in the pan direction. The captured images are processed by the NVIDIA Jetson to detect the object's center of gravity. And based on the results, we will aim to apply the control algorithms to actual spacecraft. Thank you.
This experimental setup simulates the environment of planetary rovers on the Moon and Mars. The front two views have motors and they slip when running on the aluminum ball. The rear view doesn't have a motor and it is assumed not to slip. Rovers suffer from slip on sandy terrain, which causes errors in localization from view encoders. In order to solve the problem, slip pressure estimation is applied to rovers. The slip pressure estimation is a method we have studied for driving force control on electric vehicles. At future work, we will study slip pressure estimation and control in both longitudinal and lateral directions.
Now, I will introduce the experimental setup which looks like the leg. The leg robot is connected to the rigid frame with a hip joint so that we can extract the issues belong to the leg control. The two motors are connected to each joint with a reduction system using the timing belt. This structure enables us to design legs slim and small. For advanced motion control, each joint have individual encoders in addition to the motor's rotary encoders, and the pressure sensors are implemented on the sole. We have been researching the joint torque control and legs force control. Thank you.
Okay, let's go to the next building where we have a laboratory at the basement floor that is very good for the high precision and high speed control. So they are researching on the high speed and high precision sub-control system. Because that research laboratory is on the basement floor of this building, that is kind of protected from the vibration of the earth.
Now, I will introduce one of the most important experimental setups in the laboratory. It is known that a lot of things represented by reduction gears and ball screws can be modeled as true inertia system. And this experimental setup is simulating a two inertia system with two motors and shaft. We use this ideal system to validate the proposed algorithm which considering two inertia system. And then the proposals are applied for each specific application, such as the robot actuator, machine tools, and in-field motors. Thank you. This is dual-axis ball screw-driven stage, and the experimental setup consists of two ball screws to simulate the same characteristics as machine tool. The spindle unit is now removed. However, we use this experimental setup for real cutting test. The research targeting to achieve chatter vibration, which can destroy the machine tools, and motion control such as friction compensation.
So I will introduce this single-axis ball screw-driven stage. The research objective of this stage is accurate modeling of stage structure and frictional characteristics. For the research objective, this stage has many sensors, such as two encoders on motor side and the other side, linear scale, and two displacement sensors, motor side and the other side, and roll set here. Owing to these sensors, accurate models of the stage and friction can be obtained. These models are used for precise motion control of the stage.
This is the single-axis linear stage. This stage consists of two linear motors, and the position is measured by the two linear encoders. The resolution of this linear encoder is about 1 nanometer, and the stage is driven in this single x-axis. This stage has the characteristics of the typical scan stages, so the performance of the controllers are validating in this setup. This linear stage has two linear encoders, so we can calculate the imaginary position from the two linear encoders. So, for example, the measurement point of this stage is imaginarily set at here. So this stage has a characteristic of the inverted pendulum. Therefore, this plant model has no minimum phase characteristic, and we can validate the real scanning stage characteristics. This is the setup of the 6th degree of freedom high precision scan stage.
This scan stage consists of two stages, coil stage and fine stage. Fine stage is supported by the air bearing on the coil stage, so the fine stage is floating by the air and move to the 6 degree freedom without friction. Coil stage is driven by two linear motors and measure the position by the one linear encoder. Fine stage is driven by two x-axis, two y-axis, and four z-axis Boyce-Coiled motors, and measure the position for the 6 degree freedom by the linear encoders. This high precision scan stage has the same characteristic to the industrial scanners. Therefore, we designed the new controllers and validate in this setup, and the controller is directly applied to the industrial scanners. This is the catapult stage. This stage consists of two stages, coil stage and fine stage. This fine stage is accelerating and decelerating by this coil stage. The coil stage pushes the fine stage and accelerating it. And fine stage is controlled precisely. And then after the constant velocity region, coil stage pushes the fine stage and accelerating it.
This is an experimental setup for pneumatic cylinders. We aim to replace linear motors with pneumatic cylinders. The linear motors have problems such as overheat and lack of thrust. On the other hand, the pneumatic cylinders are lightweight, low cost, and low heat generation. However, the pneumatic cylinders have many challenges in high-speed, high-precision control. One cause is a bad dead zone. We propose a dead zone compensation method with this fast response flow-meter.
I will introduce this multi-axis wirelessly powered scan stage. The research objective for this stage is reducing the effect of power cable. Conventionally, power cables are connected during power source and actuators or sensors. However, power cables cause some problems such as contamination and cable disturbance. Therefore, we replaced power cable with wireless power transfer system using magnetic resonance. The power is wirelessly transferred from power source to y-axis and from y-axis to x-axis.
I hope that all of you enjoyed the virtual lab tour today. Thank you very much for your kind attendance. If you have any questions, please feel free to contact us. I hope that you will visit us at the Kashiwa campus of the University of Tokyo in near future. Thank you very much.